Hey math fans, this is kind of a bonus lecture on Stirling's formula. Last time I just made a remark that for large n, typically around 70 or more, you can approximate the factorial by this expression right here. And it's called Stirling's formula, named kind of after Stirling, kind of after de Moivre. But today we're going to kind of use this a little bit, and I'm going to show you why and how it's used. It's used a lot in thermodynamics and data science. And let me kind of show you what this is. So actually, it's a little bit easier to work with the natural log of this expression. Okay, and that's actually a very useful way to prove Stirling's formula, which we're not going to do in this video. But let's just take the natural log of n factorial. And according to this approximation, that would be equal to the natural log of a product of three terms, right? 2 pi n to the 1/2, which is the same as the square root, times n to the nth power times e to the minus n. Okay. Now remember, what does the natural log of a product look like? Well, the natural log separates a product into sums of these three terms. So that is going to equal the sum of the natural log of 2 pi n to the 1/2 plus the natural log of n to the n plus the natural log of e to the minus n. Okay. Now remember, another property of logarithms says that you can take this power and you can really move it right in front of the natural log. So that's exactly what we're going to do. So this is going to equal 1/2 times the natural log of 2 pi n plus, and again, I can do the exact same thing with this n right here. I'm going to move that out in front, and the same with this exponent. Okay, so then we get plus n natural log of n minus n natural log of e. Now remember that the natural log of e is 1, so this goes to 1. And then we have an expression that looks like this. We have 1/2 natural log of 2 pi n plus n natural log of n minus n. Now here's the thing. This expression right here, if I can highlight, which for some reason I can't highlight. There we go. Okay, so this expression is on the order of n to the first power. It's a linear polynomial expression. This is a linear polynomial expression times the natural log of n, which is monotonically increasing, right? It's given it some heft to it. What is that? That's nothing. That's the natural log of n, and mathematicians have a running joke that the limit as n approaches infinity of ln of n is not infinity. I mean, technically it is, but it grows so slowly because that's what the natural log does. Okay, so really, speaking in the approximation for big enough n, and I mean like really big n, so I would say like probably 100 and greater, we could say that this is approximately just equal to the first two terms, which makes our approximation a lot easier. Okay. That's the term that I'm going to use today to play around with some numbers. Okay, so why is Stirling's approximation useful? Well, it's useful in chemistry, for instance, for the following reason. There's a quantity that describes a huge number of particles that we call the mole. Okay, and 1 mole of particles, these particles can be anything, molecules, electrons, whatever, that is on the order of 10 to the 23rd power. 6.022 times 10 to the 23rd power, and that's Avogadro's number, which is usually denoted capital N sub A in books. Okay, so let's suppose that in the human body, I wanted to figure out how many different ways there are to rearrange all of the water molecules in my body, just for some reason. I want to see how many different combinations there are of water molecules. Okay. Well, let's do that. So the average person in the United States of America is about 80 kilograms. It's about 80 kilograms. So average mass of a person is about, I think, 80 kilograms, which we need to convert to grams, which is 80,000. Okay, now a 10 to the 23rd number of water molecules weighs 18 grams. And if you want to know where I got the 18 grams from, take chemistry. It's the molar mass if you want to look that up. But the idea is that there's 18 grams in 1 mole of water. And in 1 mole of water, H2O, there are about 10 to the 23rd particles. 10 to the 23rd, we'll say molecules. Molecules of water. Okay? This doesn't need to be exact. I just need to get you an order of magnitude estimate. Okay, so let's see. These kind of cancel. This is roughly 20. Okay? Which makes this about 4,000 times 10 to the 23rd, which 4,000 times 10 to the 23rd is only going to increase this by 3 zeros. So that's going to be on the order of 10 to the 26th power, which is a lot. Okay, that's how many water molecules you have in your body. Well, how many different ways can I rearrange that? Well, one useful quantity is to be able to take the factorial of 1 with 26 zeros after it. So how do I take that? Let's use Stirling's approximation. Okay. The first thing that I want to do though is I want to take the natural log of this. Okay, so let's define maybe x as this quantity as 10 to the 26 factorial. And I definitely don't want to work with that. So I'm going to take the natural log of both sides. And then we have the natural log of something factorial, which we can approximate using Stirling's formula. And that's going to be approximately equal to, let me just scroll back up, approximately equal to that formula. So it's going to be, let's see, 10 to the 26 ln 10 to the 26 minus 10 to the 26th power. Okay. And we can do that fairly-ish easily, okay, right? Because we have a natural log, which means this exponent is just going to kind of move over. And we can subtract these. And we can actually use a calculator and figure this out. So I'll be right back while I do that. Okay, so when I did that, I got an answer of roughly 5.887 times 10 to the 27th power. Now you might be saying, well, what's the point of even doing that? Couldn't you just type in the original expression in your calculator? Absolutely not. I don't know of anyone that could actually do 10 to the 26th factorial, and we're going to explore why in just a minute. But this is what I got just from the natural log of this quantity. Okay, so since that's equal to ln of x, in order to solve for x, I have to exponentiate both sides. In other words, I have to raise e to both sides. And what that's going to do is over here, the e and the ln cancel, and I'm left with x is going to be approximately equal to, e to the power of 5.887 times 10 to the 27th. Now, unfortunately, that doesn't really mean a whole lot to me because I like base 10. It's called a common log for a reason. So how do we go from natural log to common log again? Well, let's see. If I have two expressions, this is like some side work over here, just to recall. So if we'll say 10 to the a is equal to e to the b, and I have b and I want to figure out what a is, I'm just going to take ln of both sides, and then the exponents move to their rightful places. I get a ln of 10 is equal to b ln of e, which is 1. Okay, so since I have, Let's see. Yeah, so I have b and I want to solve for a, so I just divide both sides by ln of 10, right? And I get that the exponent that I want is equal to b divided by ln of 10. Okay, so all I have to do is divide this quantity by the ln of 10, and I get exactly what I want. So I went ahead and did that, and I get that that's approximately equal to 10 raised to the power of about 2.56 times 10 to the 27th. So let me reiterate for you something that is applicable to the real world, which is a molar quantity of atoms in the human body, that the number of ways that those could be rearranged, 10 to the 26 factorial, is 10 with 1 with 27 zeros, number of zeros following it. That would probably take so many lives of the universes just to even express, which is why we use Stirling's approximation. Hope that was helpful.